First, let me thank the organizers for inviting me. It's good to be here in this conference. I mean, with Hubert, I only have one work. I was a PhD student at that time, and I was visiting SACLAY for a short time. So I only did a very short part of that project, but I learned a lot. And it's good to be here today. And I would like to talk about a paper that we have recently, a project that we have recently with my collaborator Tamás Gombor. It's in this archive number, maybe it still fits into the screen, and the title is medium range spin chains, medium range integrable spin chains. So what is this? I mean, this is a new family of models, which at least as a family, I would say it is new, and for which we have a new algebraic theory. We believe it is a new algebraic theory. And in this talk, I want to tell you, first of all, what these models are, what is this family, medium range models. Second, why is it important to study it? What is motivation? Why are we doing it? Then I will talk about results. I will show you results for algebraic construction, and also in the end tell you some of examples for these models if time permits. So, okay, let me start with introduction. I mean, in integrability, when we are talking about spin chains, normally or most of the times you would be doing nearest neighbor interacting models. So nearest neighbor models, where Hamiltonian is of the form, it is the summation over Hamiltonian density h, j, j plus 1. This is a two-side operator which acts on sides j and j plus 1. And the models are integrable, and we know this construction of algebraic beta ansatz or quantum inverse scattering method, how we can construct integrability properties, transfer matrices, etc. And the common property of these models is that there is a set of conserved charges Q alpha, where alpha is some kind of index, typically it goes over the integers, where these charges are extensive and they are such that they have local densities. So typically Q alpha can be written as a summation over J, some operator density, such that this is a strictly local, it's a short range operator, and we can build from these charges, we can sum them up and build a transfer matrix, and you know how it goes. We have Lux operators, Young-Baxter relation, etc., etc. Let me just point out one technical thing for my notations. I will always use alpha, this index alpha, such that the length of operator density should be just equal to alpha, and this means that basically Hamiltonian should be identified with Q2, okay, because it's a two-side operator. It's just a notation. So nearest neighbor models are, I would say, fairly well understood. What can we do with them? Then another class of models are long-range models, truly long-range models. So in long-range models, we can have spins at arbitrary distances which interact with each other, and interaction typically becomes smaller and smaller as spins are taken apart from each other. Examples are Haldane-Shastri model, or Innocenzer's spin chain, or some other models, long-range version of Hubbard model, and maybe many others. And these models are more difficult to understand. And the construction of conserved charges is also more involved, and it does not fit into this picture what we have simply here from local Lux operators. It's a little bit different. And in order to somehow understand maybe long-range models, or maybe look for other types of models, we can find a family which is between the two. And this is what I call medium range models. It is somehow in between the two. And the most characteristic property of medium range models is that we should have an extensive Hamiltonian such that the operator density is still local, strictly local, but it can be a longer operator. So not necessarily two-side operator, but three-side or four-side. For example, Hamiltonian can be written perhaps as summation over sides, H acting on J, J plus 1, and J plus 2. So on three sides. And these are the integrable spin chains that I want to look at. And I want to have some kind of more strong definition for them, more properties I require. It's very important. I want to write down three properties. So I require that they should be translationally invariant. Translationally invariant, strictly translationally invariant. I mean, this is important because with known techniques, it is known that you can construct medium range spin chains where you would have a staggering of the Hamiltonian density. For example, you take normal Lux operators of known spin chains and then you make inhomogeneities in a staggering way, like mu minus mu, etc. then you can find the four-side Hamiltonian, which is medium range maybe, but it's not translationally invariant. So I really want to look at, for example, spin-1/2 models with translationally invariant three-side or four-side Hamiltonians, for example. Important. Now, second important remark is that the Hilbert space should have the standard tensor product structure. So this is the most natural thing to do. It should be tensor product of local spaces. But it's important that I want to make this requirement. There are some models in the literature where Hilbert space is a constrained version of the tensor product, so-called constrained XXA model, or some supersymmetric models that were studied by Nienhuis, Coutens, and many others. I want to avoid those things, so I want to look at cases when Hilbert space is really a tensor product, the usual one. And the third requirement is perhaps the most important one. I want to have, so to say, new models. Okay, what is this? I just write down new. It means that these Hamiltonians that I want to obtain should not be included in the commuting charges of a known Hamiltonian or a known model. For example, here you could take a Q3 from Heisenberg's spin chain on some other model. Q3 is a three-side operator, and you could just regard it as your medium range Hamiltonian. But then it's not a new physics. So I want to disregard such cases. I want to have genuinely new interacting, or maybe free, but genuinely new integrable models. In other words, I can say that the Hamiltonian should be, the three-side Hamiltonian, for example, should be the smallest charge which exists in the theory, and which will generate in dynamics. And generally, I also expect that in these models, I will also have some kind of set of conserved charges, Q beta, which is a different set of operators than here, and beta, index beta can go over some kind of index set S, which will be typically a subset of integer numbers, but not the whole integer numbers. I mean, in a normal Heisenberg chain, you know that there is a charge for every length. I mean, here typically we will find that there will be charges not for every length, but for a subset of lengths. So this is the family. This is our definition of models, what we want to look at. As I promised, now I want to tell you why. Okay? So I erase it very quickly. So big question mark, why? And I can give you three answers why I want to look at. First one is classification. So if you want to have an understanding of what are all possible integrable models, or all possible integrable spin chains in particular, maybe you want to look at these types of models also. Then it's maybe not so good to look only at nearest neighbor models. It belongs to the set of all possible models. Maybe this is a bit academic, but still it's a motivation. The second motivation is this could be useful for ADS-CFT. And perhaps this is just a dream motivation. I mean, in ADS-CFT, the spectral problem has to do with a long-range spin chain. It's a truly long-range spin chain. But maybe the algebraic ideas that we develop, maybe they can be also used to study the long-range spin chains that come up in the spectral problem of this correspondence in the layer limit of what they have there. Perhaps it's just a dream, but I wanted to mention it. And the third motivation why I want to study are the concrete examples. So I will go to examples only at the end of my talk. I will not go there now because it would take too much time. But let me just put forward that in recent years, a couple of interesting models popped up, which are medium range models. They belong to this family that I was discussing here, and which were studied by different authors for different purposes. And the integrability structure, algebraic integrability, was not known for them. I mean, I can name as examples without discussion. I can just name the so-called folder XXA model, which was studied at least by three different groups. Group of Maurizio Fagotti and Leonard Zadnik, and then also by us, and then one more research group. It was studied for non-equilibrium dynamics, quantum quenches, and this kind of things. It's a four-side model or a three-side model, depending on how you look at it. And another important example is so-called cellular automata on light cone lattices. These are classical light cone lattices. So these are classical integrable models, but they are also interesting for quantum physics, for non-equilibrium dynamics, and they were studied a lot by Thomas Rosen, for example, and his collaborators recently. And perhaps the most important example is the so-called Rule 54 model. Maybe you have heard about it. I don't have time to discuss it. I'm just saying that when you write it down using quantum gates, it's a three-side model. And then in order to understand integrability, you would need the techniques of these medium range models that we are working on. Okay, so this is the motivation. This is why you want to look at these models. I will erase down this. And then let me go to results. So this talk is short, and I don't want to tell you all the technical derivation and how we arrive it. Instead, I want to tell you the final result of how to construct loss operators and transfer matrices. What are the key differences as opposed to nearest neighbor cases? But first, we need to review nearest neighbor cases. So because it will be a modification, of nearest neighbor models. So if you have the nearest neighbor model, you know very well that we construct transfer matrices which depend on spectral parameter U. And the transfer matrix is a product of trace over a product of Lox operators. So what we typically have is a Lox operator acting on some physical space J and an auxiliary space A, and it has a spectral parameter U. And then we have some kind of product here, so starting with Lox at 1A, then Lox at 2A, etc., to Lox at LA, and all with spectral parameter U. And trace is taken over auxiliary space. So this is monodromy matrix, but then trace is transfer matrix. You know, this is the thing that we have, and besides the Lox operator, we also have so-called R matrix, which acts, let's say, on two auxiliary spaces. It can have two spectral parameters U and V, and then R matrix can intertwine Lox operators. So we have the famous RLL relation, which looks something like this. That schematically, RLL is RLL. I will not write down now indices and spectral parameters, but those who have seen it know what I'm talking about. Using this form of Yang-Baxter relation, you can prove that transfer matrices commute. So this is the standard procedure. And then how to connect it to nearest neighbor Hamiltonian. So in order to have a nearest neighbor Hamiltonian, you need some kind of special property of Lox operator, which is the so-called regularity property. So physical space and auxiliary space should be the same dimension, and also you should have that Lox operator at specific point, rapidity 0, for example, should be permutation operator, which simply just permutes physical space and auxiliary space. If you have this, you substitute it to the transfer matrix, then you will see that transfer matrix at 0 is so-called U, I denote by U, cyclic shift. This is the cyclic shift operator along the chain. You can prove it. And you can also prove it that if you take logarithmic derivative of the transfer matrix at point 0, then you get a nearest neighbor Hamiltonian, and you will get Hamiltonian density H plus 1, which is the first derivative of so-called L-check operator acting on J plus 1 U, and this is evaluated as U equals 0. What is L-check operator? I mean, it is basically the loss operator stripped from this A. So L-check J, let's divide J plus 1 of U is P JA multiplied by normal mass. So this is the standard construction that you learn when you start to do integrable spin chains. Now you see that this is rigid in the sense that once you have this condition, then you are really destined to have nearest neighbor interacting model, and there is no way to go around it. So it is very natural to suggest that, I mean, if you want to get rid of this and you want to get interactions with longer range, 3-side or 4-side, then somewhere you should modify this area. And now we have a solution for this, how to do it. So this is the setting, and I hope I will have space, or otherwise I will erase it a little bit. Now I want to modify it such that I can have translational invariant medium range model, for example, a 3-side model. And one of the key things is that we should enlarge the auxiliary space. So this is just a result that we have. In the paper, we also give motivation why it is like this, but I don't have time now to discuss motivation. I tell you the end result. If I want to have a 3-side model, then I should take two auxiliary spaces. I should take an auxiliary space A and B, and it should, I mean, the full auxiliary space, I can denote it by big A, should be the somehow tensor product of two auxiliary spaces, small a and small b. So if we start with a spin chain model which has local dimension t, then for the free side model we should have an auxiliary space with local dimension d squared. It's just how things are. And then corresponding to this one, we will have now Lux operator. Where should I write it? I will write it here. Lux operator which acts now on physical space J and two auxiliary spaces A and B, and Lux operator still depends on rapidity parameter U. And from this Lux operator, again, what I will do, I will construct a transfer matrix with a similar formula, where instead of just single auxiliary space A, I will have two auxiliary spaces A and B, and I will take a trace over A and B. I mean, I will not write the formula, but you can imagine how it is. I will draw a figure. Maybe it is better to understand with the figure. So if a Lux operator looks like this, it acts on a physical space J and two auxiliary spaces A and B, then I need to take a product of Lux operators. So it looks something like this. No, this is just one, sorry. One here, sorry. So this is auxiliary space A, this is auxiliary space B, and I mean physical sites 1, 2, etc. J up to L, and we take eventually we take a trace over auxiliary spaces A and B, and this becomes our transfer matrix, new transfer matrix T of U. Now this is the starting point. Then we will also need generalization of R matrix. Now we have a pair of auxiliary spaces. So if we want to make monodromy matrix and commutation relations, we will need an R matrix which actually acts on 4 auxiliary spaces A, B, and C and D, and it has 2 spectral parameters U and V. There will be 4 auxiliary spaces because we will need to commute 2 auxiliary spaces here with each other. 2 pairs of auxiliary spaces, and that's why we will need A, B, and C and D. But we will have the obvious generalization of this relation, what is usually here. Now this is nice. Then what is remaining is this part. We need to find the generalization of this part, how we can find the 3-side Hamiltonian from this construction. And then instead of this initial condition, we will have a different initial condition. So Lux operator acting on physical side J, 2 auxiliary spaces A and B, rapidity 0. This should be also a permutation, and specifically a permutation which is, I have it here, PAJ, PBJ. And I think with figures it is better to understand. So when I look at this figure, when I draw the transfer matrix somehow with pictures, then Lux operator at 0 should be something like this. It is this permutation. So this is A, B. I hope this one, or maybe with the changing of A and B. So A is permuted to B, B is permuted to J, and from J you get A going outside. And when you plug this Lux operator to the generalization of this definition, then you will see that the transfer matrix at rapidity parameter U is big U squared. Remember, big U was here it was cyclic shift. So now the transfer matrix evaluated at 0 gives a cyclic shift with 2 sides to the same direction. And how to get Hamiltonian? We will get the Hamiltonian from the same formula, logarithmic derivative of U, first derivative of U basically, stripping away this factor. And from this we will get the formula. I just have enough space here. We will get the formula that H acting on J, J plus 1 and J plus 2. The 3-side Hamiltonian will be first derivative with respect to rapidity, so-called L-check operator acting on J, J plus 1, J plus 2. Derivative is taken at 0. And we need just the definition of L-check operator. And basically, L-check operator is stripping away these permutations. I'm sorry, I need to delete this to write it down. So Lux operator at JAB of U should be permutation AJ, permutation BG times Lux check JAB of U. So if I strip away these permutations, then I get the Lux check operator. And it's the derivative of this operator will tell you at the end what is Hamiltonian density acting on 3 sides. Now, basically that's the starting point. So that's the starting point, how you can get a three-side interacting Hamiltonian from Lax operators. Now, a lot of questions remain. So this is one part of the story. Second part of the story, how do you want to find proper Lax operators which have R matrices such that the generalization of RLL relation can be satisfied? So how will you find solutions to Young-Baxter relation where the solution really takes a form with these initial conditions and etc., etc. So for this we have a recipe, and this recipe also is a generalization of known recipes. Let me start over. I will delete it and I will tell you about integrability conditions. We will go back to nearest neighbor models once again. So for nearest neighbor models, when you want to classify all possible solutions to Young-Baxter relation, all possible nearest neighbor integrable spin chains, there is a condition called Reshetikhin condition for integrability. So what is this condition? There are multiple versions of this condition. I will write down one version, which is a simple version. It's actually not the most general one, but anyway, let me write down the simplest version. So if Hamiltonian is summation over J, H, J plus 1, then I construct the next charge, Q3, with a very specific formula. Namely, I take Q3 should be summation over J, and here I put a commutator, H on J plus 1, commutator with H on J plus 1 and J plus 2. So I'm enabling two-side operators. And then this is a very specific formula. If you start from Hamiltonian density, this is already specified. And Reshetikhin condition is that Hamiltonian should commute with Q3 if Q3 is given by this formula. And this commutation should hold in every volume. I mean, you can write down the local version of this commutation formula. And the condition says that if you find the Hamiltonian for which this relation holds, then it is very likely that there is a Young-Baxter integrable structure behind it, or maybe the condition says that, or conjecture says that it is always like this. So you can put it in another way. If you want to find all solutions to Young-Baxter relations which are regular, which satisfy this regularity property, then you should look first at solution of this equation, where you put an ansatz to the Hamiltonian, ansatz to Hamiltonian density, you construct this, you take commutator, and you want to see that this commutator vanishes. If it vanishes, you have a good chance of finding an actual Lax operator which produces this Hamiltonian. And this condition has been used a number of times to find solutions to Young-Baxter relation already in historical times. So, for example, I can mention a really nice work of Kennedy, who classified all SU2 invariant spin chains with higher spins, but nearest neighbor chains. And more recently, there is important work by the group of Balázs SALEUR and collaborators, where they also do classification with in many different situations, but basically going back to this idea or simple generalization of it. I mean, there is a small generalization here that came another term for Hubbard model and these kind of models where R matrix is not of difference form, but it's not so important. It's a technical detail. This formula should hold if R matrix is of difference form. But it's a technical detail. It's a minor detail. Now, what we want to do, having understood this relation, what we want to do? We want to find generalization of this Reshetikhin condition to our medium range models. So to our three-side or four-side models. And let me now again discuss three-side models. So our result is the following. It's a new result as far as I know. So we start from a Hamiltonian density where Hamiltonian acts on three sides, J plus 1 and J plus 2. And then I construct a new charge, which will be a five-side charge. It will have a five-side density Q5 of J, where, okay, J is now a side index. And this density for this operator is constructed in a very specific way. Again, it's a generalization of this one, but I want to write it in simple ways. I will not write J's. So I will just write down what is Q5 positioned at side 1. So I set this J, the side index, to 1. And then this will be commutator of H acting on 1, 2, 3, sides 1, 2, and 3, and commutator with H acting on 2, 3, 4, plus H acting on 3, 5, 4, and 5. So this will be the generalization of this formula. If you want to write pictures, I mean, if you have sides of the spin chain, then what you have is this is a three-side interaction acting on three sides, and then I want to take a commutator of this operator density with this operator density and this operator density. I mean, typically this commutator will be still non-zero because there is an overlap. So there is an overlap, the overlap of side 3. Typically, commutator is non-zero. And now our statement is that proper generalization of Reshet-taking condition is that Hamiltonian, what we get from here, should commute with Q5 in every volume where these charges fit. So in every volume which is equal to 5 or larger than 5, this should commute. There is also a local version of this if you really want. And well, it's a condition that we obtain, and this condition can be used as a guiding principle or recipe to finding medium range models. So again, how does it work? How can it work? It works in the following way. You start with an ansatz for this three-side interacting model for the Hamiltonian density. From this ansatz, you compute the five-side charge, the five-side density, and you compute the commutator. And then you want to look at parameters in your ansatz, and you want to tune your parameters such that this commutator should vanish in every volume. You can do this by hand if you want, but you can also do it in Mathematica using algebraic manipulation, or even with finite matrices if you want on, I don't know, spin chain of length 10 or smaller is already enough. And then you can find certain parameter spaces where you will actually observe integrability. And I need to stress that this is just a conjecture. So it is a conjecture even for mirror stable chains. It is a conjecture also for medium range chains that every time when we solve this relation, we actually get an integrable model, which means we can actually find lots operator and R matrix behind the model. But I need to stress that in all cases that we did, we found this conjecture to be true. So we performed classification of medium range models using this condition. And every time we found a solution where this commutativity holds, we could also later construct lots operator and R matrix. Then we just make a new ansatz and we try to find add rapidity parameter, vectorization using tricks of older works. R matrix will be more complicated, but we always found it. I mean, it seems to work. So this construction really seems to work. And with this, we have the method. So we have the method to construct these new models and understand their algebraic integrability, structure of integrability behind that. So then let me say some words about examples finally at the end of the talk. I will again erase. So we did classification of these medium range chains for three-side and four-side models with some kind of ansatz set. So of course we did not do a full classification, it's too complicated, but with certain restrictions. So one restriction was that models should be SU2 invariant. And okay, I forgot, so it should be spin 1/2 model. So spin 1/2 model, three-side Hamiltonian or four-side Hamiltonian should be SU2 invariant. There are not so many choices, and we want to see if these choices can be integrable or not. So for three-side models, what we found is that there is no new integrable model using this ansatz. I mean, we find trivial models. So in our classification, the standard Heisenberg spin chain popped up. Yeah, I mean, it satisfies also the more complicated relation that we have. And also one more model popped up, which consists of two Heisenberg spin chains intertwined. So let me explain. I mean, you can have a spin chain where the odd and even lattices, sublattices completely decouple. So you can have a spin chain where interactions are such that these sides are coupled, etc., etc. And each coupling is an x66 Heisenberg spin chain coupling. And formally it is three-side interacting, formally because, I mean, you have this interaction. but it is not a new model. I would not say that this is a new model. It popped up. In our classification, it popped up, but it's not a new model. It does not give you new physics. So we dismissed it. So when we go to foresight models, there is one new model. Surprisingly, just one, but okay, we found it. And what is this new model? I don't know the Hamiltonian by heart. So 1 second. Where is it? Let me write it down. So for this case, the foresight Hamiltonian looks like this. You have Hamiltonian density acting on sites 1, 2, 3, and 4. And Hamiltonian density is the following. It should be 2 times permutation acting on 1 and 4 minus 1 times permutation acting on 2 and 3 minus 1, and minus p permutation acting on 1 and 3 minus permutation acting on 2 and 4. And this model does not commute with x66 Heisenberg spin chain Hamiltonian, and we found no trivial way to relate it to any other model known in the literature. I mean, maybe there is a way of relating it, I don't know. We didn't find it. So perhaps it's a new model, perhaps it's a known model. Also, I mean, it was never used for anything, so it just popped up from our classification.
Okay, just a
so
kind
that's
of
one
reminder
thing.
that
then we also went further and we looked at
left.
U1 symmetric models. And by U1 symmetric, I mean that the U1 symmetry should be generated by global SZ operator. So a little bit, we want to relax SU2 symmetry and maybe then define new models. And now we also looked at, I mean, only looked at 3-side models because it already has many parameters. And for 3-side Hamiltonians with U1 symmetry, we found 2 models. And the 2 models are the following. It's written here. 2 possibilities. One possibility is actually a known model. So this model is a so-called barrier model. It is a model of a spin zigzag ladder, if you want, but it has a 3-side Hamiltonian. I will write it down. So the 3-side Hamiltonian is like this: H1, 2, 3, acting on 3 sides. It's sigma minus at position 1, sigma plus at position 3, plus the other way around. So sigma plus at 1, sigma minus at 3. And this is multiplied by 1 minus u sigma z acting on 2 over 2, just normalization.
Just a small reminder that we have still 8 minutes and maybe you want to get some questions.
How many minutes?
8 minutes.
Yeah, I think I'm at the end. Yeah, I calculated 35 minutes. Yeah. Yeah, thank you. So yeah, this is the barrier model Hamiltonian. It is a new known model. It has been studied for a long time, but we also have new information about this model because I mean the structure of the loss operator and their matrix. For this one, we have some kind of new information which I did not discuss here, factorization of R matrix, etc. So even for this model, we have new results. And the other model that we found is a new model, it seems, and we call it the hard rod deformation. Deformation of x6a. And the Hamiltonian looks like this. Where is it? H1, 2, 3. It can be written down as H tilde acting on 1, 3 times, I will write it like this, 1 minus sigma z acting on 2, maybe over 2, where this H tilde is the Hamiltonian of the standard x6a model for any kind of delta. So I will not write it down, you know very well how this Hamiltonian looks like. And basically, we show in another paper that this Hamiltonian can be understood as a hard rod deformation. What it means is that in x6a model, particles are downspins, and you have a downspin which propagates in a vacuum of upspins, and these downspins scatter, etc., etc. Here in this hard rod deformed model, the fundamental particles are 2 downspins which are turned down, and they propagate. So particles have a finite width of length 2, but you can also have a single downspin, which is an immobile particle, but it also scatters on the mobile particles of 2 downspins. But it's a topic for a separate talk. So a separate talk, I mean, in a separate paper, we also have this discussion of properties of this model. And let me just say that these 2 models are really different, but they coincide at one point. So they have a specific point where they coincide. And this specific point is the so-called folded x6a model, which I mentioned at the beginning of this talk, which was studied by Fagotti and Zabnik, and also by us. I mean, the specific point is u equals 1 of the variate model and delta equals 0 of hard deformed XXA model. And we also have results for these elementary cellular automata, but this does not fit into this such a short talk. So I think I will end here, and thank you for the attention.
Yeah, thank you for this nice talk. There are certainly questions. Jesper.
Hi Balázs, this is Jesper. So thanks, this was an interesting talk. So I understand that these integrable models are new, but what about their continuum properties? Are they conformally invariant? Are they describing new universality classes and so on?
I cannot answer this question. I absolutely don't know. So this is very fresh. So I don't even know if there can be anything new in the continuum limit. So maybe nothing. I mean, these are interesting for microscopic reasons, I would say, because really the starting point why we started to look into this is to find simple models. And it just turns out that if you want to look at simple dynamics, then sometimes the Hamiltonian should become more complicated. So let me explain. So XXA Hamiltonian is the most studied, maybe integrable model, or X66 maybe, from these spin chains, etc. But it's complicated. Beta ansatz is complicated, etc., etc. But this model that I mentioned, this folded X6A model, has more simple beta ansatz, but it's interacting. So if you want to solve quantum quenches or study some kind of interesting dynamics, and we want to have exact solution, sometimes it is better to look for more simple beta ansatz, but more simple beta ansatz requires that your Hamiltonian should be a little bit more complicated, maybe 3-side or 4-side interacting. And this is also happening for this Rule 54 model that I mentioned. And there's no time to discuss it, but it's a cellular automaton, classical cellular automaton, perhaps the most simplest interacting theory. It has soliton behavior, and still integrability structure was not known before us. And we will publish something about this soon. So this was my motivation, not specifically thermodynamic limit or continuum limit.
Yeah, right. I mean, we certainly know of a couple of cases where we have, say, 2 different integral models which are in exactly the same universality class. So it might be that even though this is new on the lattice, it might eventually be redundant somehow in the continuum limit, but that remains then to be seen, I guess.
Yes. Yeah.
Is there a way to group your sites 2 by 2 into bigger sites so that your model becomes short range?
Yes. So, I mean, this is the, I mean, we give motivation about this, and actually we write about this in our paper. I mean, who was asking? I don't know. I mean, I did not see.
Sylvain Ribaud.
Yeah, hi. So, yes, so of course, here the time was very limited. I had just this half an hour, so that's why I didn't talk about it. But actually, this idea, what you are saying, it gives you motivation of how you would end up at these Lux operators. We talk about this in the paper. And then the important thing is that eventually I want to have translationally invariant Hamiltonians. Because if you group, for example, 2 sides together, and then, of course, you are right, it becomes a nearest neighbor model. But then with this grouping, you really break translational invariance, because then once you do the grouping, I mean, the construction is translational invariant with respect to 2 sides, right? And that's the problem. So of course, all of these models, what we find here, are subsets of these grouped models, and subsets of a larger dimensional local space models in this direction. But I want to enforce translational invariance in the original chain, because this is, I mean, maybe physically more nice, I don't know. And then you need a new, little bit new input. And this new input leads to the Lux operators what I have here. So very good question. This is one way to time. Yes. Is it clear?
Yeah, thank you. I mean, just one comment. If you take a theory like Laplacian phi square, then you need 3 sides in order to construct it on a lattice. So maybe this can give you a hint. A theory which is integral over Laplacian phi square instead of gradient phi. It's not conformal, but okay. Okay, I think with this we should thank Baya again for his talk and move on to the next speaker.